still looking at similar figures here. So, guys, we're still looking at figures that are going to be the same shape, but what? Different sizes, okay? So, our job today is this. We're going to try and prove some similarity by what's known as side, 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 and then also by side, angle, side. We need to show at least 3 pairs of sides are proportional, or at least 2 pair of sides are proportional, and that the included angle is going to be preserved in all this here today. And I think that if you can understand that SSS stands for side, 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 and SAS stands for side, angle, side, I'll show you some drawings of what these look like here in a bit. But guys, our essential question today, what are 2 ways to use corresponding sides of 2 triangles to determine that the triangles are similar, okay? And our 2 ways that we're going to focus on, as I already indicated, are going to be a side, side, side setup and a side angle side setup. Excuse me. So guys, goal is pretty straightforward. We're going to use the side, side, side similarity theorem, and we're going to use a side angle side similarity theorem. Now vocabulary, I didn't put much in here. I think that this is all prior knowledge. Similar figures, same shape and what? Same shape but a different size. Do I need to write that down again? Okay. Corresponding parts. It's like which sides match up and which angles match up. Do I need to write that down for you guys? Okay. Parallel lines. Oh, parallel lines have so much in common, it's a shame they'll never meet. You guys know what parallel lines are? Yeah, they go on forever, but they never ever do what? Cross. They're in the same plane, never cross. Okay. So guys, right here is where I'm at here. I'm on this first one right here, our first theorem right here. Okay. It's called the side, side, side similarity theorem. So I'm going to blow this up a little bit so we can read that better. Let's just talk about what this says. It says the following. It says if corresponding side lengths of 2 triangles are, what's the word right here? Proportional. I'm going to underline that word. I think that's important in this definition or in this theorem. Then the triangles are similar. Basically what they're saying is if the ratio of A to B is to RS, guys, doesn't AB and RS kind of correspond to each other? Aren't they in the same general position? If that ratio is equal to BC on the bottom, as to ST, if that equals CA to TR, if all those ratios are the same, then I can say triangle ABC is similar to triangle RST. Let me put this in numerical values for you, okay? Let's just pretend we have some numbers up here. I don't know what they are. Maybe I've got, let's just go 6. And maybe this is, I don't know, 9. And maybe this is 12. I have no idea, okay? And then over here, I'm going to write down that this is 3, 4.5, and 6, okay? Kids, this first ratio, just by some of the values I put in up here, the way I've labeled this, I'm going to start looking at all these ratios right here, okay? First of all, I'll start with this one. Okay, guys, what distance did I just suggest for side AB up there? 6. So the ratio 6 would compare to what distance in the corresponding triangle? 3. So 6 over 3. We hope 6 over 3 is equal to that ratio of BC over ST. So take a look. What's BC over ST? 12 over, gosh darn it, 12 over 6. Okay. And then hopefully that equals the ratio of CA over TR. What do I have for CA? Over what? Okay. Now, kids, I think we can do this mentally. What's 6 over 3 going to reduce to? 2. What's 12 over 6 going to reduce to? 2. What's 9 over 4.5 going to reduce to? Okay, so here's the deal. If you have 3 side ratios where the corresponding side ratio is exactly the same, then we can say that those triangles are similar by which similarity theorem? Okay, all 3 sides have the same ratio. Okay, all 3 corresponding sides have the same ratio. Okay, so does that theorem make sense there first? Okay, so let's use this theorem to try and figure out example 1 here. Okay, it says using the side, side, side similarity theorem. Up here it says is either triangle PQR or STU similar to what? let's take a look at this. Let's compare STU to triangle VWX first. Okay. Let's look at the ratios in this. All right. Kids, I'm kind of looking at this triangle right here and this triangle right here. Okay. We've got two sides that are 8 and one side that's longest 12. On this other one, we've got two sides that are 20. Longest side is what? 30. So we would assume 20 is going to correspond to what distance? And 20 is also going to correspond to what other distance here? And 30 probably going to correspond to 12. Okay, so let's just set them up. Do you guys agree that one ratio has to be 20 over 8? Do I need to write 20 over 8 again? It's going to be the same thing, isn't it? Okay, so then we're going to put 30 over what? Okay, now guys, you can reduce these fractions mentally if you want to. I'm just looking at this first one right here. What number would go into 20 and 8? Which would make this a 5 over a what? 2. What number is going to go into 30 and 12? 6, which would make that again. These both equal 5 over 2, right? Now, if you don't like reducing fractions, another suggestion, just divide them out, okay? If I jump into my calculator, if I do 20 divided by 8, you really get 2.5 to 1, don't you? If I do 30 divide 12, I get 2.5. Okay? Are they the same ratio? So is STU similar to VWX? Yep. I'm going to write this right down here. STU, triangle STU, is similar to triangle VWX. By which theorem? Side, 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 similarity theorem. Okay. All right, we also need to check what other triangle, kids. So compare triangle PQR to what? Okay, so I'm going to go over here and look at some values. Looks like the two short sides on PQR are 12, right? And then two short sides here are 8. So we're going to compare 12 to what value here? 8, and we're going to compare 16 to what other value here? Okay, so let's do that, okay? So we'll do the 12 to 8 first part right here. So one ratio would be 12 is to 8 as 16 is to what here in this other triangle? Okay. Well, I'm going to divide these out just to see what I get. All right, if I go 12 divided by 8 here, kids, what do I get? If I go 16 divided by 12, what do I get? 1.3. Guys, 12 over 8 reduces only to 3 over 2. This reduces to 4 over 3. Same or different, kids? Different. Okay, so is triangle PQR similar to triangle VWX? Because the sides are not. What was the word I underlined up there in that side, side, side theorem? I'm going to write this way, because corresponding sides are not, what was the word again for me there, Reese? Proportional. Yeah, we got two different fractions, or two different ratios. I can't even spell today. Proportional. PQR is not similar to VWX because corresponding sides are not proportional. Kids, give me thumbs up, thumbs down if you feel good about the first page so far. So far, so good? Okay, do y'all have everything down so far? questions up to this point? Okay, let's roll on to page 2. Guys, these are the longest notes ever today, aren't they? Okay, let's try one right here. I really like this example right here. Okay, it says find a value of x that's going to make xyz similar to hjk. All right, no problem. Kids, how many places do you see x listed? 3. I see it in a couple of places, don't you? Okay, forget the vertice x up here on the smaller triangle. Just look at the x's in blue up there. See 2 of them, don't you? Okay, let me show you something real quickly, kids. We're comparing triangle XYZ to triangle HJK. And kids, when we've talked about finding sides of similar figures, we've had to set up some kind of a proportion here, okay? So I'm going to start with this x minus 5 part right down here. I see an x right here, okay? What would that x minus 5 distance from x to z correspond to in the larger triangle? 30. So I'm going to say that distance, x minus 5, is to 30 as, Now, take a look at your 2 triangles. Is there a pair of corresponding sides where you know the definite distances of both? 15 and 3. Now, the way I've set this up, kids, would the 3 go up top of my second ratio or in the bottom of the second ratio? Looks like I'm comparing small x minus 5 distance to a large distance of 30. So I better compare this small distance of 3 to what value? 15. Okay. I could set it up like this. Okay. Now, here's what I want to tell you. Anytime you set a proportion up like this where you have like an x minus 5 up here, always, always, always put parentheses around that binomial. Okay. So kids, what we talk about a lot in math when we talk about equal ratios or proportions is that cross products will be what? Cross products will be equal. Let me show you. Guys, you agree that 1/2 is the same as 5 over 10? What's 1 times 10? What's 2 times 5? They equal, right? So won't one cross product be 30 times 3? Won't that equal 15 times x minus 5 right here? All agree? Kids, help me out. What's 30 times 3? So I've got 90 equals 15 times x minus 5. Okay, could I divide both sides by 15 now? What would the 15s do to each other? Anybody know what 90 divide 15 is? $90 divided 15 is 6. Okay. How would you solve for x here, guys? Add 5. So we think x is equal to what value here, kids? Okay. Now here's what I would suggest you do. We think x is what value there? 11. I'm going to go over to this triangle right here. My friends, help me out. Okay, if I plug 11 in right here, what's that make this distance from x to z? Okay, if I plug 11 in right up here, what's 11 minus 6? So 5 times 5 more would make this distance of what? Okay, I would say once you found the distances that you think you know, because x is what value? I would check your ratios, okay? I'm going to go with that 3 over 15 one first. Okay, now we think this side is what value, kids? 6. What's 6 going to compare to up here? I want to know if 3 over 15 is equal to 6 over 30. And then what did we think this distance was right here? And 25 would relate to what value here? Wouldn't that be 5? Guess what's 3 over 15 going to reduce to? What's 6 over 30 going to reduce to? What's 5 over 25 going to reduce to? Guys, when I put 11 in for x, do I get the same exact ratio for corresponding sides? So are the corresponding sides proportional? So if all three sides are proportional, then this must be similar. Okay? That makes sense to you? Okay. Side, side, side similarity. You guys okay with that? Good? All right. Then, there's also a theorem called side-angle side similarity theorem, which states this. If an angle of one of the triangles is congruent to an angle of a second, and the lengths of the sides including these angles are proportional, then the sides are similar, okay? You guys see angle X right here? And angle M? What's true about angle X and angle M? They are going to be the same, aren't they? Okay. Now, you might want to write this down, but the sides that you would have to compare this side, MP, and MN. You got to have the two sides that make the angle up. Okay, so I'm going to kind of highlight these two sides. These are the two sides that make the angle up. So if I had a situation like this, where maybe this is 20, and maybe this is 24, and maybe this is 10, and maybe this is 12. Do I have all three sides this time, guys? Or do I have just two sides? Just two sides. But what I do have is this. Is 20 double of 10? Is 24 twice of 12? So the sides are proportional. So if the two sides make the same angle and those two sides are proportional, then guess what, kids? These triangles are what? Similar. Okay? So this last example right here is pretty straightforward. It says there's a diagram right here, and it's a scale drawing of a triangular roof truss. The lengths of the two upper sides of the actual truss are, I'm going to highlight these, 18 feet and what? Okay, the actual truss and the scale drawing both have an angle, or, and I should say, include an angle of what, kids? It says, is the scale drawing of the truss similar to the actual truss? They're saying the real truss looks like this, kids. I'm going to draw another triangle down here, kind of like this. They're saying the real triangle looks, oh my gosh, that might be the worst triangle I've ever drawn in my life. Forget you saw that, okay? Oh my God, you guys are probably scarred for life, you poor people. Oh. Okay, and here's the actual one that they're telling us about. Okay, they're telling you that they actually have a distance of 40 feet and 18 feet, and the angle is still how many degrees? Okay, first of all, kids, the illustration and the triangle I drew, do the sides that are labeled make up the 110-degree angle on both of those? Yes. So we need to compare 40 to what value here, kids? 10, and we need to compare 18 to what? 6. Ugh. Okay, so we're going to compare 40 feet to 10, and we're going to compare 18 feet to 6 inches. Kids, I only need to compare two sides here because aren't the included angles of the two triangles both the same 110? Isn't this like a side 10, angle 110 side setup, a side angle side setup here, guys? Okay, what's 40 over 10 reduced to? Okay, so hopefully 18 over 6 is what? But it's not, it's what? Okay. Final question says, is the scale drawing of the truss similar to the actual truss? The answer is no, because our ratios of 40 over 10 and 18 over 6, are they equal or not equal? They are not proportional, right? They are not proportional. All right, those two ratios that we got in that side angle side setup to check, those ratios not proportional. Therefore, they are not similar. Okay. So if the drawing says make it like this and the actual is made differently, is that a good thing or a bad thing? Somebody said, here's the diagram, go make this. They made one that's not similar. Is that a good thing or a bad thing? That's bad. Okay, very bad. All right. Okay, kids.